Okay, hi everyone, and welcome to this webinar organized by Satsearch. We are a marketplace that helps buyers connect with suppliers in the industry. And essentially, we wanted to put this webinar together because we saw that a lot of the people that we work with and help engage with in identifying suppliers and so on had a lot of questions on what they want to do with thrusters and propulsion, and so many different questions when it comes to what can thrusters do, and essentially because there is no single thruster as we see it that works for all kinds of mission profiles and all kinds of scenarios at the end. So we actually went out and collected lots of information from many of these teams who are building space missions, over 20 different teams actually, in looking at what was really interesting for them to know from the suppliers that goes beyond data sheets, that goes beyond the preliminary information that is out there. And then, we collected a survey and then put everything together, and we thought, okay, let's do a kind of a webinar that actually might be interesting for people to then engage with, to get this information. So we have today a panel from 5 different companies here, essentially, who are going to throw some insights based on the survey that we did to begin with. And just as a note, we welcome any of you to come in and join Satsearch by basically filling out a form, so you can essentially list yourself. I'll share the listing link at the end where you can basically click through and add yourself as a supplier to Satsearch. So you can, of course, find all of this information with all of these companies and so on here present. So to go further, let's just get on with the presentations and then move further on. So we have, I think we'll go according to the alphabetical order to kind of be more precise. First, I think to keep it kind of short and sweet and to go further on, we'll have William here from Bradford. So William, go ahead and present, and then we'll keep it short and sweet so that we can have more time at the end for the presentations. Thank you. Go ahead and share your screen.
All right, sounds great. Thanks very much. So yeah, my name is William van Meerbeke. I'm a propulsion system engineer at Bradford Space. I'm based in the Netherlands. I made this presentation together with my colleague, Wilhelm Dingerts, who is a thruster lead engineer at Bradford Space based in Sweden. So I'm going to present you the propulsion systems that we here at Bradford Space make and how you can implement it in your system, in your satellites. So first, a brief overview. So Bradford Space, we're active in many propulsion domains, going from cold gas propulsion, also electric propulsion, where we do actually everything between the tanks and the thruster. We also do liquid propulsion and more specifically, high performance green propellant liquid propulsion. And we also are involved in water propulsion. So at the moment, we have 44 propulsion systems in orbit, and we have 35 more systems delivered. During this presentation, I'm going to focus on the high performance green propellant liquid propulsion, because that's, in my opinion, most suited to small sat missions, which is the topic of this webinar. So what is high performance green propulsion? It uses the high performance green propellant, LMP103S. This is a monopropellant which was developed by the Swedish Space Corporation together with the Swedish Defense Research Agency, FOI, in cooperation with Bradford Space in Sweden. It was originally developed around 20 years ago as a higher performing green drop-in replacement for hydrogen, and that is the most common liquid propellant currently used. It is ideal for small satellites because it's environmentally benign, has very low toxicity, and it has, more importantly, excellent density specific impulse. This comes from the fact that it's liquid, so it has a density higher than water, and it has performance ISP higher than other monopropellants. So in the table below, some key differences between our propellants and hydrazine. So you see it's not toxic, or it's very low toxicity. It's not carcinogenic, not corrosive. So it's the ideal propellant, liquid propellants to work with. So this propellant has been developed 20 years ago. Also, thruster development started around that time. So it has been around for quite a while. It has technology readiness level 9. The first launch was in 2010, and the latest launch is actually happening during this webinar. So at the moment, we have 22 of these propulsion systems in orbit. During this webinar, 3 more propulsion systems will be launched. Together, that gives 50 plus years in cumulative space heritage. In terms of thrusters itself, yeah, the numbers are there. 90 thrusters, more if the launch is happening today, and with 200 years in cumulative space heritage. A lot of propellants has been manufactured and up to date, no failures in orbit. So it's a very mature technology that we want to reach out to more and more people. Yeah. A word about the thruster family. So each satellite needs a different kind of thrust level depending on your applications. So at Bradford Space, we have a whole range of thrusters from 100 millinewton all the way to 220 newtons. The most important ones are the ones which are fully colored. The gray ones are still in development. So we have 100 millinewton, 1 newton, 5 Newton and 22 Newton, which are currently in a high stage of qualification or already flying. We have 2 versions of the 1 Newton thruster. It's using high propellant, the high performance green propellant, or a slightly different formulation of the propellant, which burns a little bit colder. So these are the thrusters, but yeah, no thrusters without systems. So we also, at Bradford Space, we make propulsion systems. And also these have significant flight heritage listed on the slides. So the first one in 2010, and the latest one was in 2021, a few months ago. It was the Astroscale LSAT-D orbit debris removal demonstration. We have some propulsion systems flying soon in the coming years, and also we delivered thrusters, as you can see on the screen, to some customers. One of them is launching today. And you can see as well the propulsion system from NanoAvionics, which will be presented later on, I imagine. So also, we have flown with 6 different launch vehicles from different continents, different countries. So it's something which launch range safety is getting more and more used to, how to handle it, how to launch, which sequence of events. So it's a very mature technology, which is commonly accepted at many launch sites. But yeah, more important for you or for people who want to adopt our thrusters. We believe that our high performance green propellant systems are ideal for small satellites. We think of the range 50 to 400 kilograms. The reason it's ideal is because it's, as I said before, low toxic nature. So it's perfect for rideshare mission, Espa Grande or different ones. You don't have these toxic toxic hazard limitations. And also the loading campaign is quite quick. And this, of course, combined with the high performance and the good liquid density and storage density of the propellants. We have used or sold propulsion systems anywhere from LEO over to GEO and to orbits beyond GEO. And for our customers, they use it for all kinds of mission phases. So deployment, collision avoidance, orbit changes, direction wheel desaturation, end of life removal. That depends, of course, on the size of your satellite and the size of the thrust that you select. But everything is possible. So typically we can make it up to customer specifications, our propulsion systems. But just to give an idea, I presented here a typical propulsion system. You can see on the right an architecture. So it's a blowdown system, which has the advantage that it doesn't have too many components. So it's relatively simple, very reliable, with minimal components, but with maximum capacity and capabilities. So propulsion systems, we try to make them as compact as possible so that they can be easily integrated into the spacecraft. As you can see on the picture here, so that is our typical propulsion system, which we sell to multiple customers. And we make it in such a way that you actually can just transport it onto the satellite or into the satellite at a very late stage of integration. Just to give some numbers, to get a little flavor, the system shown in the picture has 21 kilonewton seconds. The dimensions are listed, so 530 times 520 times 150 millimeters. The nozzles are not included, so they stick out. So you have to account a little bit for that, but that's outside the spacecraft. It has 12 kilogram dry mass, can hold 10 kilograms of propellant, and just for information, typical lead time would be 12 to 14 months. So that's just an example, also to give some performance parameters. Very important, the ISP, which is a typical performance figure for these systems. So for the 1 Newton thruster, it goes all the way up to 231 seconds at the beginning of life. For the 22 Newton, it's 255 seconds. During life, since the pressure decreases, also the performance will slightly decrease in terms of ISP. The picture on this slide shows the density specific impulse. So that also takes into account the liquid density. And then you can see for each of the thrusters and compared to the baseline monopropellant, which is nowadays used, hydrazine, how it compares. Some other figures are the pressure, 24 bar at the beginning of life, 36 proof pressure. Some mechanical loads that that the system can handle are based on the HIF's specification, 14.1 GRMS and the shock 500G. Temperature, 10 to 15 degrees, and the external leak rate, which is important for launch range safety. Often it's 10 to the minus 6 in line with very high performing institutional satellites. Yeah, what to take into account when you mount this in your satellite system. So part of the high performance of this propellant is the fact that it burns very hot. So the combustion temperature is 1600 degrees, which is high for a monopropellant thruster. So that gives the high specific impulse. But the thruster has been designed in a very clever way, I have to say, so that actually the temperature, which is at the interface, is below 50 degrees. So on the plot on the left, you see the temperature at the interface at different duty cycles. On the right, you see the heat flow, which goes into the spacecraft. So it's below 4.5 watts, depending on what time the thruster is firing. So temperature is kept under control. In terms of electrical interface, when looking at the whole system, we typically provided the interface as flying leads. We think it's very easy to implement them on spacecraft level, since every spacecraft is different. So with flying leads, analog signals can be easily integrated. We are working on a dedicated electronics box where you can just command it to fire. That we're currently working on, but at the moment it's flying leads. Operational voltage is 28 around volts with a power consumption below 40 watts with 4 thrusters active. The less thrusters active, the less thrusters, the less power you need, of course. So it's relatively low power, so the payload can remain on during operation. In terms of testing, we do testing on all the components. So on all the thrusters are tested at Bradford Space in Sweden. On a system level, we also do all the testing here at Bradford Space, either in Sweden or in the Netherlands. The other components are also tested by our suppliers. In terms of operation, this is the operational box in terms of duty factor and on time, in which you can fire the thruster. So on the right, you see how hot the thruster burns. On the left, you see the plot. You see that it's actually very limited to no stay out zone. So over a very very broad range of duty cycles and on times, you can fire the thruster. So we test, as I said, all the thrusters at Bradford Space in Sweden. But it's not only on ground, of course, we have multiple systems in orbit. One of those customers, SkySat, provides information on their performance related to what they tested on ground. Quickly explain the slide. So the black dots are different firings that we did during acceptance testing at different pressures. So the x-axis is the pressure. On the y-axis, you see the specific impulse, so the main performance parameter. The red line you see is the curve through the acceptance testing that we performed on ground. And then you see two different other curves. You see the blue curve, which is from the Prisma, the first satellite that was launched, and you have the green curve, which was then done by SkySat. And we can see that the performance is higher than what we observe on ground. That is mainly due to the higher vacuum in space. We can also see it shows the same trends as what we see on orbit. So it's really validated in space and shows better performance than what we test. Last thing, also important to mention, it's a very nice to have a propulsion system, but of course you need the propellant into the system. So for that, you need a loading campaign. As I said before, it's perfect for rideshare missions. There's no toxic hazard limitations. And also the propellant loading goes quite quickly and easily. So it's a matter of days, few days, instead of few weeks for other monopropellants, especially hydrazine. You don't need, you need a bit of protection, like shown in the picture, but you don't need a very dedicated escape suit, which is very cumbersome to work in. Since the propellant is very storable, you can actually load the propellant into the system and then keep it for a few months before launch. So you don't have to load it just before launch. So for terms of operations and planning, that's very important to know. And as I said before, many launch sites have been used to accommodating us. So there's a lot of experience there. So in conclusion, I presented the propulsion system, the high performance green propellant propulsion systems that we have here at Bradford Space. They have high performance compared to other monopropellants. They can be used during all the mission phases in all orbits. We can provide a relatively off-the-shelf propulsion system, or just thrusters, of course, or we can fully customize it based on our customer needs, which we do often as well. And lastly, so it's low toxic, and that makes it more easy to do the loading and handling in all of the regulations. So that's also good to know. And with that, I want to thank you all for your attention. If you have questions, then we'll answer that at the end of the webinar, but you can also always write us or visit our social media. So thank you.
All right, thank you very much, William. So William is actually the lead systems engineer in all of this. I forgot to kind of introduce at a larger scale. So we're also doing this for the first time, so we're learning as such. So I'm sure that he's happy to kind of answer any questions. I see some questions already here, and we will take these questions at the end of all the presentations. But then, since we are also kind of keeping the Q&A at the end quite short, we're also happy to have a page at the end of the webinar where we'll have the answers for anybody who's asking questions to get their answers at the end. So just to move on to the next speaker in line, we have Dr. Lou Grimond. I don't know if that's the correct pronunciation, but hopefully it is.
That's close enough, yeah.
And he's from Impulsion, and of course Impulsion is an electric propulsion manufacturer based on FEEP technology. He's been here around with 30 years of research and development cooperation with ESA and with FOTEC. Lou himself has a master's degree in engineering as well as a PhD as well in propulsion. So Lou, with that short introduction, I hope you can share your slides and then we can move on.
Sure, I'll be happy to. Let me know if you can see everything. Should be okay.
Not yet.
Okay. I need to click share, of course. There
Go
you
ahead, yeah.
Yeah, perfect. All right. Yes, so I'm representing Impulsion here. So for those of you who don't know us, we are a smallsat and CubeSat propulsion company doing electric propulsion system based on a kind of a unique technology called FEEP. So the company has been flying thrusters for the past 3 years. We have more than 200 thrusters delivered now, and more than 60 of them in space, and more coming up every month. So one of the unique things we do at Impulsion is that we use this FEEP technology, which is field effect electric propulsion. It's a kind of electric propulsion that uses a unique propellant called indium. And indium is one of those weird metal that everybody forgets about on the periodic table. And one of the big advantages of this propellant is that it's extremely dense. It's about the density of steel, and it's solid at room temperature and non-toxic. So you will probably see this kind of theme, non-toxicity and easy to handle propellant come back a lot during the presentations. And that allows us to make a system that is debris safe with no pressure. It's literally a block of metal when it's at normal storage condition and non-toxic. So we do a full range now of electric propulsion system. So those of you who know us know probably the Impulsion Nano, which is the one that has been flying for the past 3 years. So we have more than 60 of them in orbit. It's a typical like new space product, kind of a 1U size system there. If you look at the wall range, you can see that the flip technology, so we have a relatively low thrust, but we can get to very high specific impulse and very high impulse density. So we are talking about several tens of kilonewton seconds for the micro, and for the nano up to 5 kilonewton second in something that is about 1U there. So this nano thruster, we are deriving it now into this nano R3 family, where we have been working hard to improve the robustness of the electronics, especially in terms of radiation hardness, both total ionizing dose and single event. Oops, sorry about that. And this family of thrusters, we already we are starting qualification right now, and already starting to have a delivery plan for customers during the fall and winter. So we have 3 versions of this Nano R3. So a normal baseline version, a high thrust version, that is the IR3, and then the Nano AR3, which is this thrust vectoring option that is very interesting for some people without any mechanisms. And then finally, the new thruster that we have been experimenting with for since the beginning of the year is the Micro R3, which is a larger thruster for larger spacecraft. You can see the dimension and kind of weight there. We have already one in orbit, and same thing, we are starting the qualification actually right now for the thruster. And then we have an option in development right now, which is the Micro R10, which has a high-value electronic made by the heritage electronic manufacturer RUAG, also based in Vienna. So our clients are kind of all over the world and kind of all across the spectrum of integrators, from small research labs to more prestigious research labs to new space companies, primes, traditional primes, all over the world. And that means that we have a lot of different use cases for the thrusters. So as we said, 63 Impulsion Nano in orbit, from anything ranging from a 3U CubeSat to 100 kilogram spacecraft, typically in LEO SSO orbit, and some of them beyond that. And in terms of use case, we have seen a bit of everything. Orbit raising, so we have some student CubeSat called Climb, for example, which is doing some planning to do some orbit raising. Station keeping, orbital maintenance. We have done that with ISI, for example. It's using a thruster. Debris avoidance, have an example a little bit later. And also end-of-life disposal, which is a very important topic now for spacecraft manufacturer to comply with whatever their launching organization rules are. We have launched on 5 different types of vehicles so far on 4 different continents. The fact that we ship the thrusters full filled and there's no pressurized tank or no energy stored or no chemical leak possibilities makes it very, very simple for customers to integrate. It's nothing more than a dumb block of metal when it's not heated up. So there's no really restriction on launch and ride share. And an example, for example, of use of our thrusters, we had the first flight of the micro thruster with OHB Sweden, with the spacecraft they operate called GMST. And soon after the launch, OneWeb kind of complained publicly that there was some crowded orbits where they were. And following that, there was an agreement between OneWeb and OHB to quickly move the spacecraft. So we're able to support them doing a fast commissioning and adjust the orbit of the spacecraft so that everybody was happy after that launch. And so having so many different customers means that there's also a lot of feedback that we get from them. So especially between, let's say, student teams who have little to no experience and large prime who have a lot of experience in electric propulsion and spacecraft integration in general. And that means that there has been a lot of iteration in our documentation and how we handle customers. Like an example, on the right side, you can see the user manual, where we had, I think, 3 to 4 revisions a year for the past 4 years, just to try to account for all the unique ways people want to use the thruster and have for their integration. So there's a lot of tailoring there. So I think for us, what we have seen is that there is 2 or 3 different phases that are of questions. Usually the first one is the design phase, right? People are trading between different thrusters, different missions, different operational mode. Or they already have a bus and they want to see if they can add a thruster. So our philosophy on that has been to try to keep it as simple as possible. Like you have this plug and play all-in-one system where electronic, thruster, tank, everything is contained in the same module. You just have one plug on the side, a couple of bolts, and one thermal interface that you need to keep cool, and that's all there is. But even with trying to make it as simple as possible like that, we have seen that, for example, people don't always respect the standards. Or communication can be a challenge. So there's always a loop needed to make sure that people are using the same standards there. And even if we have keep out zones, for example, on our thrusters, people always want to put things in there, which is fair because, I mean, each spacecraft is very custom made. So having a good understanding with the customer of what is load bearing, high voltage, hot, what they can do and can't do, if they need special customization option is really, really important. The second thing we have seen that is really important is have a review of mission and design with the customers, especially and whatever the level of experience actually of the customer is. Because people don't always have the propulsion vision of the system, where they might have solar panels, antennas, sensors that are too close to spacecraft, to the thruster. So that's something that is always good to look back with your propulsion provider, I guess. Also, possibilities of optimizing the firing sequences. Some people firing only during sunlight, people firing every third orbit, that kind of thing. And looping back with us, we often find solutions to have more efficient system for them. And then there are each technology has its own operating constraints. Number of restarts, okay, is it resilient to a hard shutdown? Is there EMC emission? So for the FIP technology, the nice thing is that we don't really have a plasma cloud like some electric propulsion systems. So you can operate a radio at the same time as you operate the thruster. It's resilient to hard shutdown, single event upset, and that kind of thing. And we have basically unlimited amount of restart or minimum maximum firing time. There is no limitation there. And then the last thing is that it's often the people who are actually using the thrusters are not electric propulsion expert or propulsion experts, right? So what we try to do is having a very simple and accurate thrust control mode where the operator doesn't have to worry too much about what is going on inside the thruster, the electrical parameter, and all of that. They can just control the thrust and then continuously adjust it on the fly during the mission, even during firing, if they choose to. And one of the things that AOCS engineers really want is also the possibility of thrust vectoring. So this is why we are introducing this Nano AR3 option, where especially when you go beyond LEO, where attitude control is more challenging, this option to vector the thrust is very important. Then there is integration. So one of the things is that usually people do not have the possibility to test fire the thruster on the ground at their facility, which is always a stress point because a lot of other systems can be fully tested on the ground, but not the electric propulsion system. So what we do is we offer like several different options. One is the FlatSat EM module, which is kind of an electronic box mimicking the behavior of the communication of the thruster. EQMs, which is basically a form-fit equivalent of a normal thruster. And then also training workshops, so where people bring on their electronics, their FlatSat, their flight system, and they can fire in our vacuum chamber that you can see on the screen with technicians from our company. And they can actually fire a real thruster in real time and test their script, and which we've often helped a lot with the commissioning of the thruster. And then, of course, trying to have really well-defined system checkup after integration in air. Even if you can't go to the high voltages or the plasma system, you can still do this sanity check after there. And then the simplicity of the design is also for the simplicity of integration. So as I said, we don't have any pressurized volatile propellant. So we ship them full by normal transporter companies. There's no limitation there. You can, there's no stored energy or anything there. And the only requirements in terms of integration is clean room ISO class 8 and somebody who can operate a torque wrench, basically, which is usually relatively easy to find. One of the thing, of course, is that the new space, I think, environment has been maturing really fast in terms of what the quality and requirements have been are out there. A few years ago, a lot of new space company would just take whatever, and now there's a really big push to improve the standards of productions there. And also a lot of the traditional primes are trying to adapt to this new space and come down with their requirements, sometimes a bit lighter than what they would do for a bigger mission, but still quite large requirements. And we have been working a lot with ESA and those customers to find the right compromise in terms of requirement. So that's ECSS tailoring, what everybody calls ECSS tailoring, which doesn't necessarily mean doing less work. It's just trying to work smartly, because there is a lot of standard that apply to thruster that you would design for a specific mission instead of what we do right now, which is an off-the-shelf standard thruster that goes to a lot of different missions. So I've been a lot of work to try to identify why and how we want to modify the existing standards to make them relevant to what we do. So for example, those ECSS standard QST20, QST70 on the manufacturing process, out of all the requirements, we identified 92 that were like actually relevant, and then 16 of those had to be modified to fit with like a high volume production, for example. And this is what you have to do in the end to have a reputable high volume production. So when we say high volume, we're talking about nearly a dozen thruster a month now. And to try to have an acceptance criteria that meets the quality standard of a very vast variety of clients, US, Europe, Asia, new space and traditional space, and maintain also the product quality over the time, which is always a challenge when you go from prototype to real industrialization. All right, that's pretty much on my end. And if you have also other questions, you have my email there available.
All right. Thank you very much, Lou, for that information. And of course, Lou is also super active on Twitter at Lou. So anybody who wants to have a conversation with him, of course, can do that. Lou, can you please stop sharing your screen as well?
Yeah.
Up next, we have Federico Torini. Federico is the product owner of the ExoMG propulsion system at Exotrail. And then Exotrail, of course, has a whole portfolio of products ranging from, high thrust scalable propulsion systems to mission design optimization, operation support software as well as orbital transport services. So welcome, Federico. Go ahead and start your presentation.
Thanks for the introduction, Ryan. It's a pleasure to be here. Can you see my screen?
Absolutely, yeah.
Yeah, no, I think that it's great to be here and have the possibility to discuss about this topic that is kind of critical right now, because for sure propulsion is nothing new for satellites in general. What is new is that it's increasingly becoming a must for all the satellites, even the smallest one. And as Lou, in my opinion, correctly pointed out before, we are in the situation where there are several satellite manufacturer operators that could not have all the expertise they need to deal with propulsion. And I mean, propulsion could require quite specific expertise in areas ranging from the mission design to the integration to the operation itself. So thanks for this opportunity, and let's start. So just a couple of words. Exotrail is a French company. There are close to 40 people right now at Exotrail. The objective is to be 60 end of the year. We are split between Toulouse and Massy, where the headquarters are located together with the team developing the propulsion systems. We have raised so far close to 18 million euros. With the last fundraising happening last July. What is our vision? Our vision is really to holistically improve the space agility, so to provide mobility solutions for the small satellite markets in particular. And we are trying to do so, we want to do so by relying on three main pillars. The first one being the improvement of deployment solutions. So to give small satellites a higher number and higher quality deployment strategy solutions, as well as improving their possibility to increase the performance once they are in orbit, either by optimizing the way they do operations, in particular for constellation, as well as increasing the performance of the payloads and hence the revenues for the operators. Last but not least, of course, also the mitigation of space pollution, either by giving satellites the possibility to perform collision avoidance and to the orbit, and as well as in the future to provide services to do orbit removal. We have two main line of products right now, which we think are very complementary to achieve that. The ExoMG propulsion system family, the main topic of today, and then ExOps, which is our mission design optimization operation software, which is essentially really one-stop shop, providing the operator, the manufacturer, with all the means it needs to first design the constellation, to understand which is the best propulsion solution to be implemented on the spacecraft, to define the mission plan, and eventually, of course, also to do the operation itself. We have a last development, which will become a product in 2024, which is the Space Van. So it's essentially an electric propelled space tag, so meant to embark a small sat, and after the deployment from the launch vehicle to move them in the orbit they want, and then release them, of course. So our ExoMG family is I say family because it's not really a single product, but as an ensemble of Hall effect thruster propulsion systems. So nothing new. Hall effect thruster technology is a quite old technology that first flight in the 70s with the Russian thrusters, and it's I would say always based on 4 blocks, which in our case are really building blocks because of our modular approach, meaning that all the configuration that we made are always based on the same electronics and fluidics. The fluidics being the module distributing the propellant from the tank to the thrust head, which is the module actually generating the thrust, and the electronics managing the power coming from the satellite and treating it in order to feed the thrust heads. So we have, let's say, 2 variables to make our configuration. The first one is the tank. Depending on the delta V needs of your mission, we can choose the proper size of tank. We have a family of pre-qualified tanks. And the second variable is the thrust level, which can depend on the size of your spacecraft and your mission needs. We have, to tackle this, we have 2 thrust threads, one 60 watts class thrust thread and one 150 watts cluster thread. And then we do clusterization with the micro, so up to 4 micros. In this way, as you can see here, we have a pretty wide range of performance we can offer. In terms of thrust, we can go from 2.5 millinewton with the Nano up to 30-35 with a cluster of 4. In terms of total impulse, we range from 1 kilonewton second up to 250. In this way, we can meet the needs of platforms ranging from like 10 kilos, so 6 CubeSats, up to 250 kilos. A couple of words also about what we have done and reached so far. We successfully performed our IOD mission with NanoAvionics platforms and last year, where we nominally performed, a characterization of the system, maneuvers, ignitions, and also characterization of the performance that was actually higher than expected. It was good, honestly. And hopefully in 9 days, we should be again in space with an aerospace platform on the Falcon 9 Transporter 2 mission. This is a pathfinder of an upcoming Earth observation constellation from Aerospace Lab. And we are also about to deliver 2 other systems to Clyde Space. And those one will be embarked on the HALO 3 and 4, which are the pathfinders of the Eutelsat Internet of Things constellation, HALO. Then we have also other projects ongoing with institutional customers, several, ranging from the ESA-CNES, the European Commission, the French government, as well as also with other commercial customers. So now diving into the central topic of today. First of all, I will need to be a bit quick, but no worries. We'll share the material afterwards, and you will have all the time to see all the details of the different slides. So was really to give an overview, which is the typical, time frame and time scale of a project with us. I say a project because we would like really to have this approach that supports the customer from the really beginning to the very end. This is also complemented by XOPS mission design, indeed. So the definition at the beginning of which are the requirements of the propulsion system, depending on the needs, and to the end, to the operations. So coming back to this point, if you have a company and that company doesn't have the expertise, all the expertises it needs to implement propulsion, the idea was to have all the means we needed to give them the possibility at the end to enable the possibility of propulsion on board of their spacecrafts. So the standard package we want to offer is not just about the hardware. It's all it is needed from A to Z. And just if you need some specificities, depending on the project, we can add other options, increasing the flexibility of the package, meaning additional milestones, extended data package, higher quality, additional tests, whatever. With the same philosophy, here I wanted to show a bit some possible LEO use cases. I defined these through our software, XOPS. And the point is that propulsion is quite key within the overall constellation project. I'm saying so because properly defining the proper propulsion technology and performance could have a huge impact in the overall business case. I can take two examples. For example, let's say that you don't have a propulsion system capable of performing post-launch maneuvering. This will force you to rely on rideshare launch. And so you will not sure to be in the proper operational orbit slot you want to be. You need to go to a dedicated, and in this case, the cost you need to pay for the launch will be higher. So this is a parameter you should take into account really at the beginning of your the definition of your project. Second example, for example, it's the time to orbit. Let's assume that your propulsion system has not the proper level of thrust. This could translate in, let's say, 1 year of time to get to the operational orbit after the deployment. If your small sat have just 5 years of lifetimes, this means that you have reduced of 20% your total revenues and delayed your revenues of 1 year. So this is why it's quite important to accurately account for all these elements since the beginning. And this is also why we want to offer not just hardware, but also all the software you need to perform these trade-offs, which I mean, was expertise to do that is not easy to get there, either in terms of time and money. So this is why they think that as a propulsion provider, we need to give these tools and not to have these tools already within the company, the customer. This is a bit, I showed before some use cases ranging from low maneuver capabilities to very high maneuver capabilities. Then the second parameter you need to account is the size of the platform. And depending on these two variables, we can define which is the proper XOMG configuration could fit your use case. And this is an overall map of what we can offer and how we can meet the different needs in this sense. The second degree of flexibility we offer with XOMG is that through our modularity, we are not forced into one single form factor. So once we have defined the performance you want for your mission, we can then define a form factor that fits seamlessly in your platform volume constraints. Another step we wanted to took at the really beginning was to simplify to the maximum extent the interface, as also Lou pointed out before, in terms of mechanical interface, electrical interface, thermal interface. Quite often with propulsion you have problems deriving from dissipation. So this is the reason why we put quite a lot of effort in the decoupling to the maximum extent, the thrust thread, not to have too much dissipation towards the spacecraft, to offer several options in terms of a communication protocol, in electrical interface, as well as I mentioned before, the flexibility to have different form factors. Another important point, we decided to follow this envelope approach. So using a qualification envelope covering the majority of the launch vehicles available in the market, so to be compatible with as most as possible platforms and launchers. Then this is, for example, the standard offerings we have. Then, of course, you have the possibility to customize it. This is a pretty standard functional vibration, TIVAC, and functional test. Then, depending on your needs, we can introduce additional tests. For example, on the right, you can see the full coupling test we perform with the NanoAvionics platform, which was something we wanted to do with our first customer to mitigate any risk coming from EMC or other possible, any other possible interactions between the propulsion system and the satellites. Usually around the community, there are some concerns about the utilization of liquid propellants and pressurized systems. that this can be true, but just if you have not done your homework in advance. So what we have done is to perform all the analysis we needed to be sure that at the end the customer will have absolutely no troubles in terms of range safety and transportation with our systems. So our baseline is to deliver the propulsion system already filled. Then if you need it, we can offer several options, both to sell you directly in the xenon filling machine we have designed, either to provide you with directly the xenon filling service. And in terms of range safety, we work to be sure that we are compliant with all the launch pads available around the world, from Europe to US to India to Asia. So to not have any hurdles coming from these 2 points. In terms of integration in the platform, together with our standard offer, as I showed before, we offer also support during integration. The system is made to be very, very easy to be integrated on the platform. So you just need the standard ISO 8 clean room. We offer with the system also a very easy plugin software to check the health status of the system after integration. So I would say that you do not require any specific expertise in-house to integrate the system. In terms of space operations, we have several projects ongoing to provide thrust vectoring by 2023. No problem to operate the propulsion system while payload operation. Of course, as a disclaimer, you need to be in the proper attitude to operate simultaneously both the payload and the thruster, and you need to have you need to have accounted for the proper energy balance overall. And I would say that is everything. So thank you a lot for the attention, and I will available to answer any question you may have.
All right, thank you very much, Federico. So we do have a tremendous amount of questions. So for the panelists here, if possible, of course, at the end, we might not have all the time to get all the questions. So I do recommend that if you do have the time, I already see William doing it, where he's answering some questions directly on the chat. So with Lou and Federico as well. So if you have any questions that you think you can answer directly on the chat,
Perfect.
Please feel free to do so. That way we can cover more ground that way as well. Perfect. So we will then now go to Hyperion with Bert here. So Bert has a PhD in electrical engineering from TU Delft and was one of the co-founders of Hyperion, which was recently acquired by AAC Clyde Space, and he continues to manage Hyperion. So welcome, Bert, and please share your screen and get.
Good afternoon, all of you, and I'm very grateful for Satsearch on organizing this nice webinar on propulsion. And actually the webinar was called a little bit different. It was called Adopting Trusted on Small Satellite Missions. And in a way, I felt a little bit inconvenient with that title because we don't provide propulsion. What we provide is an orbit control system, and when actually not a system, a solution. We want to provide our customers with a solution that solves all their problems, whether it is orbit control for deorbiting, whether it is constellation control. We try to think from the customer lines, and that means that we made a system, well, of course it looks very nice, but it's taking off all the problems you could have using propulsion. So that means it is of course, it is safe, it is green, it is customizable, it has high trust, it doesn't hamper the use of your other system, it has everything by itself already organized in the way you would like it to be as a customer for your satellite mission. You want to have a system that is a fire and forget, and that is how we started with this system, and that is how we came up with this propulsion unit. I want to mention here that we did this development and are doing this development together with Dorn Aerospace. So if you have any questions, you can either address Hyperion Technologies, OSC Clyde Space, or Dorn Aerospace as well. If you look at the heritage that we have, well, we have TRL 9. We have it available as a product already for quite some time. It is easily customizable. If you now would order it, you have a lead time of approximately 6 months if you have one unit. But if you want to order multiple units, that can also easily be ordered. In the end, it is about what do you want as a customer. So we are having developed this system in order to be able to provide you a solution that can be customizable for your satellite, but also can be manufactured in larger quantities, in small series. So if you want to say, I want to have a constellation in the next 1.5 years, that's also possible for us, based on all the manufacturing technologies that we use, like additive manufacturing. Of course, I told you we can use the PM200 for about everything. So that means deployment, phasing, collision avoidance. But in the end, it is about how easy is it to use it. So if you look at our specific PM200 system, you can typically look into the system as a fire and forget system. You don't have to command it for every single small detail. The main part is that you say what you want it to do and it does it for you. That means if you want to have a deployment, the command should be do deployment. If you want to do phasing, it should be as smart as that it can do phasing. Having the generic knowledge of your constellation, knowing what it has to do. So we want to make it as simple as possible, both in the operations as well in the integration into your satellite. So if you look, for example, we have thrust vector control. So that means that you don't have very strict requirements on your attitude control system. It should be able to correct itself if you have thruster misalignments. And mind you, we are not thrusting for a very long time. So we have a significant higher thrust than most of the propulsion systems for small satellites. We are chemical propulsion, so we are typically looking at propulsion thrust levels of 0.5 Newton to 1 Newton. So that means we need to have thrust vector control. And again, this is fully integrated. It is a full solution. You want thrust, you get thrust. You don't have to bother about anything else. And of course, your satellite is not the same satellite as the satellite of your neighbor or your previous one or your next one. So we want to integrate. We want to integrate with your mission. We want to make it simple for you. So we support you in doing the calculation. What kind of system do you need? Do you need a larger tank, a smaller tank? Do you need a little adaptation of your thrust? We do the testing for you. Of course, we can do testing of the total impulse. And we can do everything without third parties. Everything can be done in-house by Dawn Aerospace and Hyperion Technologies. If you look at flight heritage, our system has been launched in 3 different systems. So the qualifications levels meet those of Vega, Falcon 9 and Soyuz. So that includes everything from qualification of the units, including safety requirements, but also ground support equipment. As you know, we have a chemical-based propulsion system, so it needs to be fueled, and that can be done as safe as you would imagine, either at your premises, at the customer premises. It can be transported, being fueled. You can do it yourself. We can do so. That is again completely focused on what would be most convenient for you as a customer. Well, here you see a couple of examples. The fueling can be done at our premises. It can be done at your premises. We can support you. We can bring people from either Dawn or Hyperion to your premises to do the fueling. And we are using propellants that are, say, just industrial-based gases. So you can get those fuels and anywhere in this world. So there are no single restrictions in using our propulsion system. As you can see, this is also a system that is suitable for 3U CubeSats. It can be very small, even for a chemical propulsion system. Makes it very convenient to adapt it to your specific requirements. If you look at the integration, because that was one of the questions, how about integration of your propulsion system? Well, we think it doesn't start with integration. Integration is only the last part of your design. The first step is to think about how does it fit your satellite. And from that, the integration process should be a logical next step. We will, of course, ensure that your satellite can easily accommodate our propulsion system, whether it is from a mechanical point of view or whether it's from an electrical point of view. We are providing a number of, say, standard electrical interfaces. The unit will be easily integratable because it is a 3D printed structure, can easily be adapted to specific mounting studs, other mounting options. In the end, it needs to be at the outside for propulsion, but that would not be a surprise. If you're talking about thermal interfaces, there are no real relevant thermal issues with our PM200 propulsion system. If you look about the thrust level, it is most likely that the thrusting time will be in the order of a couple of seconds. That is already so much more the thrust in total than you would have with the electric propulsion system, that there is no significant thermal problem to be expected. There is no incredible heat increase. So there are no significant things you should take into account during your satellite design. Makes it very easy. You can just plug in the propulsion unit. For AIT, actually the same holds. We are using normal industrial gases. You could test it in your lab. No special requirements. Of course, they are gases, so you should be a little bit careful. But actually, if you are able to give a barbecue for your friends, you should be able to also apply our thruster system. If we look what we learned from previous missions, well, fueling at a factory works fine. We can do it, we can ship it. It can be shipped with air freight, no problems with it. We can understand that you want to do it if you are going to large quantities yourself. That's also possible. We can train your personnel either at our premises or at our customers' premises. Shipping works well, either fueled or non-fueled, and we are very supportive in the sense that if you need to have things being transported, we can fill out all the forms for you. We have experience in all the paperwork required. So anywhere where you want to have it, we can ship it within, of course, the allowed countries to ship to. Training, what will you need? And that's a good question. And I think any good system would only require common sense. Yeah, of course, you should know about your satellite. You should know about your mission. You should know what you would expect. We can support you in your mission design, but again, we provide you with a solution for your orbit control. So we can think along your lines about how much should your tank be? How should your thrust procedures look like? Are there special requirements to your satellite bus? Well, the answer is a full no. We don't need very high voltages. We don't have a high power consumption. Only during the moments that we are thrusting, we need something like 10, 15 watts, which allows for full operation of your satellite also during the operation of your satellite. So actually, this is a system that gives you no headache and just do your orbital changes that you want. Of course, we're talking about standards. That is not something you should be concerned about. That should be our concern. So we're concerned about it, and we have ensured that it is ECSS compatible for the relevant aspects. Mind you, we are a new space company, so we don't say it is designed according to ECSS, but we do comply to all the important ECSS regulations with, for example, tank pressures, reliability, etc. Test philosophy. All our systems will be tested before they will be shipped to you. So there will be there can be an incoming inspection at your end, which is similar to our outgoing inspection. We have functionally tested our systems. And of course, if you have your system in-house, you can do also testing of the propulsion system. And that should then be easy, because if you have your system, you don't want to have very cumbersome setups for testing your propulsion system. If you have a simple vacuum, and we are not talking about an ultra deep vacuum. If you have a vacuum, anything below 200 millibar, which is I would say any lab should have, you can do already your testing of your propulsion system with real gases, with real firings, and you can really see how it operates. We could, of course, provide you with an engineering model that gives you a touch and feel of how the system would look like, how it operates. You can test it for a day, a week. I don't know how long you want to test it. You can fuel it yourself. So any test that you would like to do, we can provide you with an EM that allows you for all the testing you like to do. Easy also for integration with your flat set, because you can see all the interfaces from an electrical and software point of view, see if they are working. So try to work with it, with this system, and you will see it is just as easy as I'm explaining you right now. Then about facilities, what would you need? Well, simple vacuum chambers. What did we do about it? Comparing to what you could do and what we did. What we did is, of course, we did vacuum chamber hot testing. We did hydrostatic testing for your tanks. Can they withstand all the pressures? Is it safe? We did hot fire testing, many more than you will probably do, because we want to ensure that it works. Not now, not next week, always. So we do a lot of testing on our test systems, but also on your system to provide a system that works when it arrives at your site. One of the questions we got was, can the thrusters work while, or can your payload work? No, there are two things. The thrusters have thrust vector control. As mentioned, we have a large, our thrust is about 1 Newton, half a Newton, 1 Newton, a little bit more, a little bit less. So yes, we do need thrust vector control. It is automatically included in our systems if required. And not all our systems require thrust vector control. It is an add-on because we don't want to make it more expensive than necessary if you buy one of our units. So if it is required for your mission that you have thrust vector control, it can be included, and it does it automatically without interaction with your OBC, with your ADCS, whatever. It's a fully autonomous system. Then you do your thrust maneuvers, and can your payload still operate? And the answer is a full yes. Because if you look at the operation of your payload, what you can see at some propulsion systems is that a lot of power is required, either for a short amount of time, either for a somewhat longer amount of time. We don't need to heat up catalyst bed. We don't need a continuous power for electric generation. What we only need is, say, about 10-15 watts for this moment that we are now thrusting. And that is only, say, 10-15 seconds, and that is sufficient. So our power requirements are very limited. I think that gives you a little bit of the highlights of our propulsion solution. I would say orbit control solution. If you have questions, we are very willing to provide you some answers during the Q&A later in this webinar. Thank you very much.
Thank you again, Bert, for this very nice presentation. Again, as I mentioned, I'll of course, bring up your own to come up as well if there's any questions to be answered. But if you do have the chance and if there is a possibility to answer some questions that are open for you, please feel free to do so. Now we're going to quickly move together to Armando from NanoAvionics. Armando has a background in aerospace engineering and has R&D experience from Spain, and then currently works at NanoAvionics, which is a small satellite bus manufacturer, and has done over 85 successful missions. So Armando, welcome to the stage, and yeah, go on, please. Thank you.
Hi, thank you, Narayan. So thank you for Satsearch for organizing this webinar. I'll be walking you through the NanoAvionics EPSS. This is a development that we've done internally. So who are NanoAvionics? Who are we? We're a global prime provider of wide applicability end-to-end small satellite constellation technologies. And our main aim is to provide the market with an economic and viable range of small satellites for constellations and in general for other businesses that want to get into the space sector. Our philosophy is to pre-integrate these buses and satellites and pre-configure them. And in that, within that activity, we've developed our own propulsion system with some partners that are present here, for example, Bradford. The company is now based in Vilnius, Lithuania. That is where the headquarters are. We've now also got offices in Columbia, Illinois, and in Basingstoke, UK. We're over 100 strong now, and we've got AAT facilities in all of our various offices. So the EPSS propulsion system, enabling propulsion system for small satellites. It's a bit of a mouthful, so we decided to stick with EPSS. This is a blowdown type ammonium dinitramide ADN based green monopropellant system. We developed this system through various EASY projects, and the standard configuration carries a single propellant tank with a single thruster, and it provides about a Newton of thrust at beginning of life. We've gone with a very modular design approach with this propulsion system. It is part of our design philosophy for all of our subsystems and platforms. So we chose to go this way in order to give flexibility to our customers with configurations. More than one thruster is available to our customers should they choose to have that configuration. The sizes go from 1.5 units to 3 units in volume, and the impulse can go from 1 to 4.5 kilonewton seconds. The wet mass is between 2 and 4.5 kilograms, and the delta V capabilities or the impulse capabilities can be adjusted based on your mission profile. So depending on what you want to do and how you want to do it, we will be able to tune those capabilities based on specific mission needs, but still maintain an average specific impulse of around 220 seconds. So that's more or less within the range that we have tested for, which is 214 seconds to 220 seconds. This propulsion system has flight heritage in several of our missions. Lituanica Sat-2 and M6B are the most notable ones. We got successful flight heritage there, and we are going to be flying this propulsion system in multiple upcoming missions over the next 2 years. We have fully qualified this propulsion system using ECSS standards. This has allowed us to a very extensive and successful qualification campaign, and we did multiple hot firing test runs for this system. It is pre-qualified and flight ready for a variety of mission profiles. We'll go into that a little bit later. And our partners have, we know that our partners have tested the thruster itself to more than 45,000 pulses at thruster level, and we've tested it to about 1,000 pulses at system level. So what kind of mission profiles? The short answer is anything that requires a thruster. As we know, most of the market is going to be needing thrusters more and more, regardless of size. So we have designed it where you can either look at formation flight for constellation deployment, track compensation and orbit maintenance, orbital maneuvering, synchronization and positioning of communications equipment and payload instruments, obviously end-of-life purposes and deorbiting, and propulsion component development and production. So if you're doing a very specific mission that requires custom-made propulsion systems and custom-made configurations, we can also kind of develop that and make sure that you can create a spacecraft that can help other spacecraft move around. We can also help in full system development and production for custom developments. In general, this thruster, in terms of in-orbit operations, can be used with the payload on, but this will depend entirely on your power budget and the size of the satellite. It all kind of revolves around the duty cycle, but yes, it can be fired with that payload on. How to use it? Well, we have implemented a very simplified and flexible approach to this. The user sequences through different system states by using commands only available in a particular system state, and this ensures the system is not operated in any improper way. Also, the system is protected by multiple layers of safety features, whereby the system will continuously monitor the health of the propulsion system and inhibit activation of any of the actuators of the system should there be a case where non-nominal values are detected. So how have we done how do we do the assembly, integration, and testing, and the quality assurance of this thruster? Well, we do a lot of component level testing. Each individual hydraulic component is individually accepted for functionality and leak tightness after assembly. So we will ensure that all of these components have no faults and they will be operational. Each individual thruster is also separately hot fired in order to measure its performance by our partners at Bradford. And each propellant tank is pressure tested and inspected via non-destructive inspection to ensure that there are no leaks to that pressure tank. All of the accepted components are then integrated as a system. Each hydraulic joint is verified for leak tightness, and this includes welds or elastomer seals. Then we do a full propulsion acceptance test campaign with appropriate mission-specific environmental loads. So this includes the functional testing, making sure all of the electrical interfaces work. We do pressure testing, we also do vibration testing, and we do thermal vacuum testing. The thermal vacuum testing is something that we have managed to develop within our own premises. We did a couple of hot firing test runs. On the right side, you see the thruster firing up. It's quite a cool image in my opinion. This is a run that we managed to do where we got a single continuous pulse for more than 15 minutes, while also maintaining 1 Newton of stable thrust. The single sessions that we've done end up having a cumulative time of over 44 minutes of firing, and that includes the over 1,000 pulses. Usually, we've noticed that chemical propulsion testing capabilities are limited in Europe, and the pandemic kind of forced us to kind of look at other solutions. So we built and used our own testing facility for covering this sort of testing need and any future needs that we may have, which is quite cool. We've got extensive experience as a company in dealing with propulsion systems, chemical and electrical. We've actually also worked with Exotrail and with Impulsion before, so we are very comfortable in integrating this sort of propulsion system, whether our own or another partner's. We have multiple past missions that have had propulsion systems on them, as well as many upcoming missions. As I think we've mentioned, there's been a general theme throughout. There's more and more missions that are going to require this sort of systems on board. We effectively managed to demonstrate the green monopropellant in the Tuanica Sat-2, and in M6B we also demonstrated the mission control side of things and propulsion control side of things quite successfully. Future missions will include our larger systems, the C2 and the C3 configurations. We follow ECSS standards as well as any mission-specific requirements. So we work under slightly modified ECSS to better suit our needs, but we try to not modify that standard too much so that we're compliant with that standard all the time. There's also some product-specific requirements that have been derived from all this testing and staying to the standard that have allowed us to kind of get a very, very nice custom-made process under that standard. Here we have some performance metrics. On the left side, you've got the propellant tank pressure versus the propellant consumed. The propellant consumed would be the x-axis and y-axis propellant tank pressure. As we consume propellant, the tank pressure will drop, as you can see. And the graph on the right is steady state vacuum thrust versus propellant tank pressure being the x-axis and thrust being the y-axis. Now, this is a counterintuitive chart. We are going to start at a higher pressure, and then we're going to move to a lower pressure. So what we do notice is that at the beginning, as you can see at the beginning of life, the thrust is around 1.1 newtons, and it will go down as we lose pressure in the tank by expending some propellant. The next graphs show steady state specific impulse versus propellant tank pressure. So as you can see, that indicates us the range of specific impulse that we can get. But the important graph that I'd like to focus on is the graph on the right, where we can see the average specific impulse on the y-axis and the pulse length on the x-axis. What this graph shows is that if we do short pulses, we will get a lower specific impulse, and if we get longer pulses, we get a higher specific impulse. This allows us to work with the customer and adapt to your mission parameters and mission profiles based on what you may need to find that optimal kind of pulse length based on the level of efficiency you need, or the level of the length of pulses you may need during your mission. How do we integrate our thruster into our spacecraft? Well, our requirements specifically for this thruster would be an ISO class 8 room, clean room or better. We can be present for the integration to help out our customers integrate into their platforms. We should also note that we've gone for a very kind of easy to integrate design. It's pretty straightforward. We just use some screws on the interfaces here, and then we just bolt it onto the platform with a relevant thermal surfaces in the right place. It's more or less 20 to 24 screws. We also require a little bit of kind of thermal, let's say, savvy. We need to understand your thermal conductance and operating temperature requirements, and we will also need to kind of see how your thrust to heat radiation would affect your platform during firing. This needs to be considered, and the thermal requirements are, as well as the thermal interfacing surfaces, have to be kept below 40 degrees Celsius during system operation. And we also need to consider the plume, which is basically the exhaust around the nozzle. And if it's placed next to certain components, there has to be a little bit of analysis done in order to determine what the thermal loads are, or if there's going to be any potential contamination to any sort of sensitive material you may have next to the thruster. In terms of training, we can provide training to all of our customers. We will actually train you in loading procedures, hot firing sequences, and general system operation. As I mentioned, we can also be present during integration. And I was going to say, let's have a Q&A, but we'll have a Q&A right after. So thank you for listening. My email for any questions you may have that we can't cover during this webinar due to time constraints is just there. It's armando@nanoavionics.com. Thank you very much for listening to our presentation.
Again, thank you very much, Armando. I think that's very insightful. We do have some time for Q&A, and thank you very much, everyone, for keeping up the time. So I'll just go with one round of Q&As, and then the rest of them, we have them saved, all the questions, so people can get those answers on an article that we will put up together so that all the questions are addressed. So we'll go through the same order as such. So William and Wilhelm, so maybe I'll ask you first. Can you share something on cold starts and preheat temperature? That's one part of the question. So you want to address that?
Can you see me?
Yes.
Yeah, so cold starts are not possible. You need to preheat the reactor of the thruster to roughly above 350 degrees C. Typically, we recommend a 30-minute preheating time, and it's with a 12 watts nominal. But for emergency cases, you can reach correct preheating temperature within 10 minutes for certain operational modes of the using the heaters.
Right.
So emergency heating is available, or emergency heating is possible.
Right, and the second question that I have for you is, what is the propellant used in the 1 Newton GP thruster? Is it different from the one used in the 1 Newton HPGP?
Yeah, so there is a slightly lower temp blend, but it has the same. It's also an ADN-based propellant. It has the same components, but at different ratios. So it still falls under the same transport classification, but it has a slightly lower combustion temperature. But there is also in development a GP thruster which has a shorter life, but can use the high temp or standard propellant LMP103S.
All right, thanks. So move on to Lou here. So Lou, there's two questions again for you. One is, why do you use indium and not xenon?
Sure. I mean, it's based on the technology that we have. So feed thrusters need propellant that is liquid. So we don't have any valve or pressurizing system. It's purely capillary feeding. And people have been experimenting with different liquid metals. Indium has been a good compromise for us in terms of temperatures, reactivity with other materials. And also reactivity with air and humidity. So we are not sensitive to that, and we are not eating the spacecraft through corrosive reactions, for example. And so we can't use xenon also. So that's for the feed process. Yeah.
Oh, sorry, I was muted. So the second question is, what are the common problems that you face, during testing?
What are the common problems we face during testing? During acceptance testing, typically it's a pretty streamlined process now. What have we seen? So each, the thrust of the actual direction of thrust, for example, for each thruster is measured for thrusters. And sometimes if somebody has like a very strict thrust pointing requirements on the thing that we'll need to swap the thruster to the next one in line. But this is also why we have this system where we don't necessarily assign a thruster from the beginning to a specific client. We will have just produced thruster continuously, and you can then and then we just pick one up from the assembly, basically, or assembly line to assign to a client. So we have had client dropping a thruster during integration, and we were able to provide a replacement within 2 weeks to the customer for the integration to the spacecraft. So usually any small hiccup is relatively streamlined for us on that.
Right, thanks. So I'm going to move on to Federico. So Federico, there's a generic question here that you might throw some light on, which is what do you see in terms of trends, in terms of demand and requirements, and how is it different for the primes versus researchers versus startups versus so on?
Yeah, actually, it's a nice question. I would say that in the last year, 1.5 years, I mean, apart from the overall evolution that we have witnessed within the space market with the advent of the new space, I would say that with the maturity, I mean, not the maturity still, but the development of all the different new launchers, meaning the fact that if you see relativity, the electron neutron, all the smallsat launchers from Germany, we are moving towards a slightly higher payload capacity. And these together with the decrease of the overall launch cost, I would say that is moving a bit the platform average size towards, bigger satellites. So while 2 years ago, all the new advertised constellations were planning to rely on 3U, 6U, 12U CubeSats. Now all the new announcements points at between 40 kilo, 100 kilogram satellites. And this is of course a trend that has, I suppose, a huge impact on us as propulsion providers. So generally speaking, I would say that the commercial space, I think will move, and for commercial space, I mean more constellations, will move towards bigger satellites, while probably the academia, everything we develop for a CubeSat will remain there, will remain available for academia, for Pathfinders. But concerning commercial application, I would think that there is the interest in moving towards slightly bigger platforms. Also, for example, regarding just the lifetime, I mean, if you have the possibility to have each satellite remaining in orbit for 2 times the time as before, you just double the revenues. So there is for sure a trade-off. and the launch cost is definitely a parameter you need to take into account. And with the degrees of launch cost, it's clear why you won't like to have bigger platform.
Right, thanks. So I just have a quick follow-up here. This seems to be super specific, which is how do you deal with thruster-induced torques?
It was for me, Narayan?
Yes.
Yeah, I mean, of course, from the beginning, the design of the electronics, the truss threads, and the system as a whole is made not to induce any sparks. And on top of that, also in the qualification process, you need to de-risk this possibility through specific testing.
Right, thanks. So I'm going to move on to Bert and Jeroen here as well. So Bert, there's somebody who asked that could you elaborate on why is it sometimes not a good idea to fuel at the launch site?
I would like to pass that question to Jeroen.
Yeah, so it's mainly a matter of, I would say, peace of mind, scalability, and also budget. So in a launch campaign, any launch campaign, but especially the rather complicated ones where you have a lot of different satellites and payloads being launched, time is very critical. So there's a very, let's say, time critical, stressful operations with a lot of stakeholders involved. Whereas if you can move this to the factory of either us as propulsion supplier or at the integrator of the satellite or the factory of the end user, the satellite operator, things can be done, in normal time zones with a fewer amount of stakeholders involved. And now it can also be done way ahead of time. So I think, this is an attractive feature of our propulsion system. I noticed a few other of the technologies discussed here today feature this as well. And I think everyone who has been involved directly or indirectly with a satellite launch campaign will recognize that time at a launch site is much more valuable and much more stressful than time at your own facility. So the more you can do ahead of the launch campaign, the better, and propellant loading is one of these things.
Right. I have a just quick follow-up, Jeroen, as well there, which is, this has come up a lot of times where people are asking, can you provide attitude stabilization during the firing of thrusters?
Well, it depends a bit what is meant with that. So as Bert described, the standard PM200 has a two-axis thrust vector control system. So any disturbance torques that the thruster itself or the operation of the thruster induces on the spacecraft, those are compensated for. Now, this can also be expanded to actually induce torques if you want to use it to quickly slew the spacecraft. Beyond that, I think Bert also mentioned it, of course you can use the thrust vector control to a certain extent to also unload reaction wheels or for any rotation in general. However, it does cost propellant, whereas for most operations in LEO, you can do this with wheels and magnetorquers where, at least from a propellant point of view, it's a free operation. So that's probably the best thing to do.
Thank you again. So we are running out of time, so I'll quickly move on to Armando with the last couple of questions before we close. So Armando, there's one, again, specific question on, are the tanks on the EPSS, propulsion system, expulsion, or they used PMS? I'm sorry, I'm not a propulsion expert, so I'll leave it to you.
So the way it works is we have a membrane inside the tank where on one side we'd have the propellant and the other side would have a pressurant. These are not mixed, and then the propellant is expelled as you fire the thruster. So it's all a pretty simple design.
Right, and let's say the last and final question is, we've seen today an array of technologies presented here. And there's green propellant, there's cold gas, there's feed, there's Hall effect thrusters, and everything else. So, I mean, you're also having the perspective of a kind of a system integrator at the end, right? So how do you think all of these technologies and the whole market will evolve in the next, let's say, 5 to 10 years? Armando?
You cut off a little bit there. Can you repeat the question?
Oh, sorry. I said we've seen today a lot of different, propulsion technologies presented, right? And then you're also a system integrator, so you see something from that perspective as well. So how do you see this trend evolving in the next 5 to 10 years with all of these different technologies?
Well, I think we've mentioned it in snippets here and there. Over the next 10 years, there's definitely going to be a move, regardless of size of platform, towards having propulsion on board. But what type of propulsion will depend entirely on your mission and what you want to achieve, and how. Different types of propulsion will give you different mission profiles and different ways to operate in orbit. So it's not a question of whether or not there's going to be propulsion on satellites, however small or however big, but rather what type of propulsion. That's what we're seeing, and that's where it's going.
Right. Thank you again, for that insights, and I thank every one of you for having done all the preparation, because I know that this was very demanding in terms of the preparation, because we sent out all of these surveys and shared with you a lot of the specific details that we wanted to have presented in this place. So of course, so for anybody who's still here around, you can of course, file a request to talk to each one of them individually. We can happily pass them on to you, and then you can have individual conversations to connect with them. And of course, all of these presentations and the material here will be available recorded and will be available for anybody to listen in again or to share with your colleagues or so on. I see that, we have had about 59 questions. So we've had half of them or more than half of them answered directly or through this conversation. So, but then we will have all of the other questions collected and then answered and available on Satsearch for people who have attended and can go through these questions in case we were not able to cover the entire ground at the end. So just as a last bit, we also have our Slack community at Satsearch, so you can join us there to keep in touch with us for the future webinars. You could also listen to our podcast, where we have almost everyone here talk about the technology trends and what is happening in the market through that. Or you can get in touch with us, be on our newsletter and get in touch with us. We hope to, of course, collect feedback from both the team here presenting as well as the people who are listening in, to see if this is a good idea to do more of this, and then hopefully this will help the entire industry moving forward. So thanks again for everyone for being a part of this. I'm really grateful. The team at Satsearch is really grateful for all of you for this tremendous amount of preparation. And I hope everyone who attended got something out of it, and everybody at the end of this has been richer in knowledge moving further. And thank you again, everyone. And I hope you have a very nice evening.